Hello, and welcome to this Chemistry World webinar, Broadband Benchtop NMR Spectrometer Spectroscopy. It's more than just protons. I'm Philip Broadwith, Chemistry World's business editor. For those of you not familiar with GoToWebinar, just a little word about the platform we're using. It's an interactive platform, and one of the biggest things about it is you can ask questions, and we really want you to. That's how we think you get the most value out of these sessions. There's a box near the bottom of the GoToWebinar panel, which by default is on the right-hand side of your screen. If you type in your questions, they will go to our speakers, who you can see on screen at the moment, Robin and Claire, and they will be answering those questions both during the webinar by text and in the live question and answer session at the end. It's a really important way to get some really good information from our experts, so please ask away. Don't wait until the end of the webinar. If you've got a question, just drop it in that box at any time. If you miss any part of the presentation, or you just want to watch it back again in your own time, pick up on some details, then we'll be sending everyone a link to the recording in a few days' time. And to say thank you to everyone who attended the webinar live, we'll also send a certificate of attendance in that same email. Today's webinar is about using benchtop NMR to probe a variety of different NMR active nuclei, including some of the slightly more exotic ones beyond proton and carbon NMR, such as phosphorus, lithium, boron, silicon, that kind of thing. From pharmaceuticals to battery research, teaching, all sorts of areas, having access to a broadband spectrometer right there in the lab can give you opportunity to get some really unique insights into the chemistry that you're investigating. We've worked with Oxford Instruments to bring you some really important information that we think you'll be interested in from some real experts in this area. Today's presenters are going to be handing back and forth a little bit as the presentation goes on, so I'm going to introduce both of them at the same time and just let them go on from there. We'll be hearing from Robin Blagg, who is an application scientist at Oxford Instruments. He has a background in organometallic chemistry. But first up, we've got Claire Dickson, who is an application specialist at Oxford Instruments, and Claire has a wealth of experience developing NMR methods and techniques. So I will now hand over to you, Claire, and we'll go into the main presentations.
Welcome everyone, and thank you, Philip, for the kind introduction. Hopefully you can now see our slides.
Yes, we can.
Brilliant. So today we're going to have a look at broadband NMR spectroscopy and how the Oxford Instruments X-Pulse benchtop NMR spectrometer can be used for applications involving a wide range of NMR active nuclei. Initially, I'll introduce the X-Pulse instrument, then Robin and I will take you on a tour of various nuclei which can be observed on the X-Pulse, looking at how the observed spectra differ from common proton NMR spectra and covering applications of the different nuclei. We'd like to start off by asking you a couple of questions, so I'll just hand back to Philip to bring up the poll.
Okay, so as Claire said, we're going to have a couple of polls just now, so I'll ask Chris to just launch that one. Okay, the first question that we're asking is, which of the following nuclei have you previously measured NMR spectra for? You can select multiple options, so select all of the ones that apply to you. We've got proton and or carbon 13, fluorine 19, phosphorus 31, lithium 7, or something else. So as I say, select any and all that apply to you. Just a quick reminder for anyone who missed the first couple of minutes of the webinar, you can ask questions at any point during the course of the webinar, and we will be sending out a link to the recording of the session, the whole session, and a certificate of attendance later on. So we've got quite a good number of votes coming in. I'll just leave it open for a little bit longer. Do remember to check out all of our other upcoming webinars on chemistryworld.com/webinars if you're interested in this, and some more webinars coming up. I think we're getting to the point where there's not so many more votes coming in. So Chris, I'll ask you to close that poll and we'll go on to the second question. We're going to be giving you the results of these polls a little bit later on in the session. So we're just going to go through both questions now. So the follow-on question is, how many different nuclei would help you to fully characterize a single sample? So which ones would you like to be able to measure? You can only select one answer for this. So just one nucleus, for example, just proton or just one other type of nucleus. 2, for example, proton and carbon. 3, proton, fluorine 19 and carbon, or some other combination. 4, proton, carbon, fluorine and phosphorus, or any other combination of nucleus, or would you want to look at 5 or more different nuclei at a time? So you can just select one of those answers as we go through. Okay, and yeah, as I was saying earlier, you have the ability to ask questions at any time during the webinar, and when Robin and Claire are not presenting, they're going to be looking at those questions as they come in and answering any that they can during the session. Otherwise, they may be able to get back to you by email afterwards if we don't get through them either during the session or in the Q&A session at the end. Okay, I think we're getting towards the point where not so many more people are voting now. So Chris, I'll ask you to close the poll and I will hand back over to Claire and Robin to continue the presentation, and we'll see the results a little bit later on.
So to move on to the next part of the webinar, while I expect that many of you are already familiar with NMR, for those who aren't, I'll briefly walk through a simplified version of the fundamental processes to provide a general understanding. We start with the concept that all nuclei exhibit a fundamental property known as spin. The vast majority of nuclei have a non-zero spin, giving rise to a magnetic moment for each nucleus. This is where we get nuclear from. A bulk sample contains many nuclei and the spins are randomly oriented. When we apply an external magnetic field, there is a preferred orientation for the spins to align, and with a majority of spins aligned with the magnetic field, a net magnetic moment results. This is where our magnetic comes from. Once we have spins aligned with the magnetic field, we can start to manipulate them to retrieve useful information. To do this, we use one or more radio frequency pulses. The pulses rotate the net magnetic moment of the sample, making it resonate, giving us the resonance of NMR. This rotation of the magnetic moment induces an electrical current in the detection circuit and can be measured as the sample relaxes back to equilibrium state. This gives us the basic NMR signal, a free induction decay, or FID. Repeating this loop generates more signal by combining together multiple FIDs. Then you apply Fourier transform to the FID, generating the typical NMR spectrum. When you think about NMR spectroscopy, you usually think about a large cylinder as seen on the left. This contains a high-field superconducting magnet cooled by liquid helium and liquid nitrogen. Alongside that, you will have another large box that contains all the electronics required to collect data. Maintenance of these systems usually requires the use of dedicated facilities and personnel. With benchtop NMR, as the name would suggest, we can shrink that system down so that it can fit on the bench in a conventional lab. Our design philosophy uses the same approach of separating the magnetic and electronics console to ensure the best possible performance while still retaining a small form factor. So inside the box on the right, we have the electronics, and inside the box on the left, we have our permanent magnet, and this is where you insert the sample. While we describe the X-Pulse as a benchtop instrument, in practice it's usually mounted on a mobile workstation, permitting the instrument to be located in the optimal site for different applications. NMR spectrometers are usually described by the strength of the external magnetic field, which for NMR is typically reported as the proton resonance frequency. For the X-Pulse, this is 60 megahertz. However, there are other indicators of an instrument's performance and capabilities which should always be considered. Signal resolution is quantified through peak widths of a standard sample, and for X-Pulse is a maximum of 0.35 Hz at half height and a maximum of 10 Hz at the height of the carbon satellites. Sensitivity is again quantified using a standard sample, and when fitted with our broadband probe, X-Pulse has a minimum signal-to-noise ratio of 130:1. While sensitivity is correlated to a number of parameters, including the nuclei of interest and the magnetic field, it's also an indication as to the quality of the electronics, since a major source of noise is from the electronics and is minimized through keeping our electronics separate from the magnet. In practice, the instruments leave our factory with a significantly better performance than these values. Additionally, the X-pulse comes with field gradients and shaped pulses as standard, allowing for a range of advanced experiments to be performed, many of which we'll discuss today. Like most modern high-field instruments, X-pulse is a 3-channel spectrometer. This means it can simultaneously excite and/or observe 3 different nuclei. The 3 channels cover different frequency ranges. The first is the deuterium lock channel, the second is the proton fluorine channel, and the third is the broadband X channel, capable of observing a wide range of nuclei, which are often referred to as X nuclei. The X-pulse can operate at variable temperatures using a gas variable temperature system. It can be fitted with a flow cell to allow for online monitoring of chemical processes and has a user removable probe to make cleaning and recovery from broken tubes, which we all know happens occasionally, as easy as possible. Besides his years of high-field NMR experience, my colleague Robin Blagg has a lot of experience running spectra of different nuclei on the X-pulse. I'm going to pass over to him to tell you about the capabilities and potential of broadband benchtop NMR spectroscopy.
Thank you, Claire. Before we take a look at some NMR spectra, we'll look at which nuclei are NMR active and consider what parameters affect how good a nucleus is for observation by NMR. One of the greatest strengths of NMR spectroscopy is how, with the correct hardware and experimental parameters, it's possible to obtain NMR spectra of almost all known chemical elements. Initially, we can consider all 118 chemical elements on the periodic table. However, many of these elements are radioactive with no stable isotopes and, quite frankly, the domain of particle physicists. And while, in principle, it may be possible to make NMR measurements of some of these, doing so would be non-trivial due to small half-lives and hazards associated with working with these species. The next consideration is which elements have sufficiently abundant isotopes with non-zero nuclear spin, which, in principle, can be observed by NMR. In fact, all but a handful of these elements have at least one such isotope. This gives us 73 elements which, in principle, may be observed by NMR. Now, the choice of hardware comes into play. In the case of the X-pulse, in its standard hardware configuration, we can observe at least one isotope for 31 of these elements, shown here in orange. Of these elements, those which we have demonstrated as observable on the standard production X-pulse, many of which we will discuss today, are shown in dark blue. These include hydrogen-1, i.e. the proton, carbon-13, fluorine-19, phosphorus-31, and silicon-29. While the choice of hardware affects which nuclei can in principle be observed on a given NMR spectrometer, the physical properties of the nuclei, and indeed the properties of the resulting chemical compounds, are important considerations of the ease of observing such signals in practice. The major physical considerations are the natural abundance of the relevant isotope and its gyromagnetic ratio. The natural abundance of a specific isotope recognizes that in nature, most elements are a mixture of isotopes of varying abundances, and if we're concerned with a low abundance isotope, such as carbon-13, which is only around 1% of all the carbon in nature, you'll only be able to observe a subset of the total amount of the element present in your sample. The gyromagnetic ratio is a physical property associated with each nuclei and can be viewed as an indication of how strongly a given nuclei will interact with an external magnetic field. It is from the gyromagnetic ratio that the frequency a given nuclei is observed in a particular magnetic field may be calculated. Indeed, upon its discovery, one of the first applications of NMR was to measure the gyromagnetic ratios of different isotopes. But more on that later. Considering the natural abundance of an isotope, its gyromagnetic ratio, and the NMR experiment itself, it is possible to quantify the ease of observing a specific isotope by NMR. This is the receptivity of an isotope and is commonly reported relative to either proton or carbon-13. The other physical parameter which influences the NMR of a given nuclei is the magnitude of its nuclear spin. While all nuclei with non-zero spin are NMR active, the value of that spin affects the nature of the observed signals, as we'll see later. These parameters for selected NMR active nuclei of interest to both NMR spectroscopists and the wider chemistry community are shown here. Before we go into detail, though, on the various NMR active nuclei, we'll have a look at your answers to our poll questions.
Okay, Chris, can you just bring up the answers, please? So the answer to the first question, which of the following have people already measured? Perhaps unsurprisingly, mostly proton and carbon, but a good spread of the other answers, fluorine, phosphorus, lithium, and a few others. Is that more or less what you expected, Robin?
I think that's pretty much what we would have expected. As I said, we spend a lot of time talking to battery people, so normally we'd perhaps see a slightly higher level at lithium-7, but it'd be interesting to see how many of those other nuclei are ones that we're going to have the opportunity to look at today.
Great. And Chris, the answers to the other poll, please. Okay, so how many would people like to? Predominantly some combination of 2 nuclei, but a good number of people again wanting to be a bit more flexible, have 3, 4, or even 5. Again, is that as you might expect, Robin? Or
I think that again is pretty much as we'd expect. It's very much an indication that yes, a lot of chemical characterization is limited to organic compounds, where you are pretty much looking at what I'm almost certain is going to be proton and carbon, but recognizing there are a fair number of other systems out there where you are looking at, you said 3, 4, 5 or more. In my past life in academic research, I certainly, as a matter of course, was very much in the 5 or more category for virtually everything I worked with.
Brilliant. Okay, well, I think we can safely go back to the presentation. So, Chris, if you just drop off the thing, and we'll carry on with the presentations. Thanks very much, Robin.
Thank you. Right. While the title promised that NMR spectroscopy is more than just protons, we will start by looking at proton NMR spectroscopy. In order to identify the various features of an NMR spectrum, which are applicable to all one-dimensional NMR spectra, whatever the nucleus. All the NMR spectra we'll look at today, with a couple of exceptions, which I will mention at the time, were collected on a single standard configuration X-pulse broadband benchtop NMR spectrometer. The signal actually measured by a modern NMR spectrometer is the free induction decay, or FID. This is the sum of all the frequencies that make up the NMR spectrum, undergoing a pseudo-exponential relaxation over time. The study of these relaxation processes is known as NMR relaxometry and is an entire field in its own right, underpinning such applications as magnetic resonance imaging, or MRI. However, in spectroscopy, we're concerned about the frequencies within the FID. In order to extract them, the time domain FID undergoes a Fourier transformation to give the frequency domain NMR spectrum, which you're probably already familiar with. This spectrum is of a simple small molecule, ethyl crotonate, and comprises 5 signals, corresponding to the 5 chemically unique proton environments in the molecule, each made up of multiple distinct peaks. Each of these signals can be uniquely assigned to one of the proton environments in the molecule by consideration of various features of the spectrum. You may have noticed that while I've described the NMR spectrum as being a frequency domain spectrum, the x-axis is in units of ppm. These are in fact parts per million of the frequency of the nucleus on the instrument, and this is known as the chemical shift scale. The reason for using a chemical shift scale is that it is independent of the field strength of the instrument. If a proton shows up at 1.2 ppm on a 600 MHz high-field instrument, it will show up in the same place on a 60 MHz benchtop instrument. The relevant chemical shift range is dependent on the nuclei and choice of reference compound. For proton NMR spectra, where 0 ppm corresponds to the signal of tetramethylsilane, or TMS, the majority of signals for diamagnetic, organic, and organometallic compounds fall within a range of +15 to -5 ppm. The chemical shift of a signal corresponds to the local chemical environment within the molecule. In this case, there are signals corresponding to saturated hydrocarbons, esters, and vinylic protons, corresponding with the chemical environments in the ethyl crotonate molecule. The next major consideration is the area of each signal. NMR is an inherently quantitative technique, where the area of the signal corresponds to the amount of the nuclei present in the sample. In the case of a pure sample of a compound, as we have here, this means that the integrated areas directly correspond to the number of hydrogen atoms in the molecule. In this case, distinguishing the methyl, methylene, and methine groups. This can be further extended for mixtures of compounds to accurately measure the proportions of various chemical species by NMR spectroscopy. The final major feature to be considered, and one of the great strengths of NMR spectroscopy, is the splitting of each signal into multiple peaks. This arises due to scalar or J coupling with other nearby NMR active nuclei. In the case of ethyl crotonate, all the splitting we can see here is caused by coupling between protons. J coupling is mediated through bonds, and if one proton is connected to another proton through just a few bonds, splittings can be seen in the spectrum. In general, the fewer the bonds, the stronger the coupling. These splitting patterns can be predicted. One way is to apply the N+1 rule for spin-half nuclei like protons. N-equivalent neighbors will split a resonance into N+1 peaks. For example, in an ethyl group, the CH2 is split by CH3 into 4 peaks. Conversely, the CH2 splits the CH3 into 3 peaks. The relative intensities of these peaks can be predicted using Pascal's triangle. Thereby, the classical triplet has 3 peaks in a 1:2:1 ratio, while a classical quartet has 4 peaks in a 1:3:3:1 ratio. More complex coupling schemes can arise due to coupling to multiple magnetically inequivalent nuclei, such as the doublets of quartets for the 2 vinylic protons. The magnitude of the J couplings can be measured directly from the spectrum, and for proton-proton couplings can be up to 18 Hz. Since J couplings and peak widths are fixed in frequency, their widths on the chemical shift scale used in NMR spectroscopy are dependent on field strength. For example, the methylene signal at 4.1 ppm has a width of around 25 Hz on a 60 MHz 25 Hz. On a 60 MHz instrument like the X-Pulse, this is a width of around 2/5 of a ppm, while on a 500 MHz high field instrument, this would be around 1/20 of a ppm. This difference leads to some of the clearest visual differences between NMR spectra obtained at various field strengths. Considering chemical shifts, the integrated signal areas, and the peak splittings, it is possible to unambiguously assign the signals observed in the proton NMR spectrum of ethyl crotonate to the chemically unique hydrogen environments in the molecule. While in the case of this simple molecule, the spectrum could be assigned without considering all of chemical shifts, integrations, and couplings, for more complex systems, often they will all need to be considered, potentially also requiring the use of additional advanced 1- or 2-dimensional NMR experiments. In fact, even a very simple molecule can give rise to a complex NMR spectrum, as shown in this proton NMR spectrum of bromotrifluorobenzene. While there's only a single chemically unique hydrogen environment in the molecule, in the ortho position relative to the bromine, giving rise to a single signal in the spectrum, the peak splitting of the resulting multiplet is highly complicated. In part, this is due to coupling of the protons with the fluorine atoms in the molecule, although there are other effects which affect splitting patterns of multiplets, particularly at low field, which are well beyond the scope of this webinar. On the X-pulse, as with most high field systems, the proton channel is also able to observe fluorine due to the similarities in their frequencies. While most signals in a proton NMR spectrum fall within a 20 ppm range, fluorine-19 NMR spectroscopy requires a much larger spectral window, with signals commonly observed over a range of +100 to -250 ppm, relative to trichlorofluoromethane. Fluorine-containing compounds are used in a huge range of applications, including pharmaceuticals, bulk chemicals, and electrochemical devices such as batteries. Considering this fluorine-19 NMR spectrum, we can clearly observe two signals in a 2:1 ratio, corresponding to the two chemically unique fluorine environments, meta and para. While the multiplet arising from the metafluorines is complicated, the signal arising from the parafluorine is clearly recognizable as a triplet of triplets, with the larger 20 Hz J coupling arising from a 3-bond coupling to the adjacent fluorine atoms, and the smaller 6 Hz coupling from a 4-bond coupling to the orthoprotons.
So we'll start by looking at what is probably, after the proton, the second most commonly studied nucleus by NMR spectroscopy, carbon-13. This is despite the fact that due to its low natural abundance and gyromagnetic ratio, carbon-13 has the lowest receptivity of any commonly studied nuclei. Arguably, it is only because of its importance in organic, organometallic, and biochemistry that NMR spectroscopy of carbon-13 isn't a small niche field. In fact, it can be argued that much of the development of NMR spectroscopy over the past 60 years has been focused around making it easier to obtain useful information from carbon-13 NMR spectra. It's the ability to apply these developments in hardware, pulse sequence design, and data processing to a modern benchtop instrument that is one of the greatest strengths of the X-pulse. The simplest carbon-13 NMR spectrum is a standard one-dimensional spectrum. Like we've already seen for proton and fluorine-19, the example on this slide is the spectrum of ethyl crotonate. One of the first things you may notice is that each of the 6 chemically unique carbon atoms in the molecule only gives a single sharp peak in the spectrum, with no multiplets arising from coupling to other nuclei. This is not because coupling doesn't take place, but because carbon-13 NMR spectra are generally obtained proton decoupled, removing the carbon to proton splittings, greatly simplifying the spectrum and improving the signal-to-noise ratio. The second feature of carbon-13 spectrum that you may notice is that despite each signal corresponding to a single carbon atom in the molecule, the peak intensities and integrated areas are not equal. This isn't implying that carbon-13 spectra can't be quantitative. However, the proton decoupled one-dimensional carbon-13 NMR experiment, as usually performed, isn't. It should be noted that the ester carbon with no directly bound hydrogen atoms in brown gives a clearly less intense signal than the other 5 carbons which have bound hydrogen atoms. Since we can't usually rely on integrations or J couplings for the assignments of carbon-13 NMR spectra, there are other commonly used approaches both to aid in assignment and to compensate for low receptivity. Examples of these approaches include the use of 2-dimensional proton-carbon correlation experiments and advanced 1-dimensional experiments such as the distortionless enhancement by polarization transfer, or DEPT series shown here. Both of these approaches partially overcome the low receptivity of carbon-13 by actually exciting the high receptivity protons, with the sequences then transferring the magnetic polarization to and observing the NMR signal of the carbon-13. In addition to the sensitivity enhancement, These advanced experiments can also tell us additional information about the source of the signals. For the depth series, the presence or absence of a signal combined with its phase, that's whether it's positive or negative, allows for signals from CH3, CH2, and CH carbons to be distinguished. In the case of the two-dimensional proton-carbon correlation experiment, which is a multiplicity-edited heteronuclear single quantum coherence, or HSQC spectrum, the cross peaks identify directly bound carbon and hydrogen atoms, and the phase of those peaks distinguishes methyl methine groups in red from methylene groups in blue. Similar to carbon, silicon has a low abundance and receptivity, and so benefits from many of the same NMR techniques as developed for carbon. Silicon-containing compounds in the form of polysiloxanes or silicones are used for a huge variety of applications, including as adhesives, lubricants, and sealants, along with uses in medicine and in the home. Both the monomers and polymers can be readily characterized by silicon-29 NMR spectroscopy. Together with carbon-13, silicon-29 is amongst the lowest receptivity nuclei studied by NMR spectroscopy. In fact, despite a slightly higher receptivity, the standard one-dimensional NMR experiment gives even weaker signals for silicon-29 than for carbon-13. This can be demonstrated by comparing these proton-decoupled 256 scan spectra of 1 mol per liter solution of hexamethyl trisiloxane. The dark blue carbon-13 spectrum clearly shows a sharp singlet for the 6 methyl carbons in the molecule, while in the yellow silicon-29 spectrum, signals corresponding to the two silicon environments can only just be made out. In the same way as we've already looked at for carbon-13, the use of more advanced NMR experiments, particularly those based around the excitation of protons and polarization transfer, are commonly used for the collection of silicon-29 NMR spectra. We've already looked at depth experiments where they were used to distinguish between different numbers of hydrogen atoms bound to a carbon. Appropriate parameter choices allow us to do the same thing for silicon. The depth 24 spectrum was obtained with a parameter choice which selectively shows signals associated with silicon bound to 2 methyl groups. In this case, that's both chemically unique silicon environments in the molecule, while the depth 90 spectrum used a parameter choice which only shows silicon atoms directly bound to a single hydrogen atom, and hence only the peak associated with the terminal silicon atom is observed. A sequence which we haven't seen so far is the spin-lock polarization experiment. This shows all silicon signals coupled to one or more protons without the need to select specific experimental parameters, as was done with the depth series. Since effective sensitivity enhancement takes place when obtaining two-dimensional correlation spectra, proton-silicon spectra are also commonly used in silicon-29 NMR spectroscopy. In this case, a heteronuclear multiple bond correlation, or HMBC spectrum, shows cross peaks for indirectly bound silicon and hydrogen atoms. For this molecule, this is through 2 bonds between the silicon atoms and the hydrogens of the methyl groups. Alternatively, an HSQC spectrum could be obtained, which would show a single cross peak for the directly bound silicon and hydrogen atoms at the indicated position. We now move on to nuclei with a much higher relative receptivity than carbon-13. After carbon-13, phosphorus-31 is probably the second most commonly studied X-nuclei by NMR spectroscopy. Phosphorus-containing species are commonly used in organometallic chemistry and hence catalysis. They are ubiquitous in many biological processes and also used in many household products and foodstuffs. Like carbon-13, phosphorus-31 NMR spectra are usually obtained proton decoupled, with signals observed over a spectral range of +200 to -250 ppm. Since unlike carbon, most phosphorus-containing compounds only contain a small number of phosphorus atoms, the resulting sharp signals are usually easily distinguished and can vary significantly with only a small chemical change. This can be shown by looking at the phosphorus-31 NMR spectra of triphenylphosphine in green at the bottom, triphenylphosphine oxide in blue, triphenylphosphite in red, and triphenylphosphate in brown at the top. These compounds have effectively identical proton and carbon NMR spectra arising from the phenyl rings, and yet can be readily distinguished by their phosphorus 31 NMR spectra. An important application of phosphorus 31 NMR is in quality control of reagents. These compounds, for example, will gradually oxidize over time from phosphorus 3 phosphine and phosphite compounds to the phosphorus 5 phosphine oxide and phosphate. And since the signals are clearly distinguished, not only can the presence of an impurity be identified, the quantitative nature of NMR also allows the amount of the impurity to be measured and monitored over time. Another common use of phosphorus-containing compounds are as weakly coordinating anions. For example, the use of hexafluorophosphate as an anion in lithium-ion batteries. Hexafluorophosphate is an octahedral molecule with the phosphorus atom surrounded by 6 equivalent fluorine atoms. Therefore, applying the n+1 rule and considering Pascal's triangle, you'd expect to see a septet in the phosphorus 31 NMR spectrum, with the signal made up of 7 peaks with relative intensities in a 1 to 6 to 15 to 20 to 15 to 6 to 1 ratio. And that's exactly what's shown here. Since you can observe the coupling in the phosphorus NMR spectrum, you'd also expect to observe it in the corresponding fluorine-19 spectrum, as shown here in green. Since the 6 equivalent fluorine atoms are coupled to the single phosphorus atom, the observed signal is a doublet comprising 2 peaks of equal intensity. In the same way as we would usually decouple protons when obtaining a phosphorus 31 NMR spectrum, we could choose to decouple fluorine-19, which for hexafluorophosphate results in a single sharp peak.
Next, we'll look at boron 11, one of 2 NMR-active isotopes of boron. Boron-containing compounds have a range of applications, particularly in organic synthesis, such as in Suzuki cross-coupling reactions, and as Lewis acid catalysts, and are often used as weakly coordinating anions. Unlike the nuclei we've looked at so far, boron 11 is a quadrupolar nuclei. That is, has a nuclear spin greater than 1/2. Without going into the quantum mechanical details, there are some major observable differences in NMR spectra of quadrupolar nuclei compared with the spin-half nuclei we've already looked at. The first is that in general, the line width of the peaks will be broader, with the width of the peaks very dependent on both the size of the molecule and the symmetry of the boron center. The second feature of note is that J coupling is not always observed for quadrupolar nuclei. The first boron 11 spectrum we'll look at is that of the tetrafluoroborate anion, a small tetrahedral molecule comprising a boron atom bound to 4 equivalent fluorine atoms. As we've already established, fluorine-19 is a 100% abundant spin-half nucleus. So you shouldn't be surprised to see in the boron 11 NMR spectrum the 5 peaks in the 1 to 4 to 6 to 4 to 1 ratio of a pentet. Since boron-fluorine coupling is observed in the boron 11 spectrum, you would also expect to see it in the fluorine-19 NMR spectrum. And again, that's the case. However, up to now, we've only seen coupling to spin-half nuclei, where the n+1 rule applies and the peak intensities can be calculated using Pascal's triangle. In that case, like the hexafluorophosphate spectrum we just looked at, we'd have expected to observe a doublet, comprising of 2 peaks of equal intensity. That's clearly not the case for coupling to boron 11. While coupling to a single spin-half nucleus splits a peak in 2, coupling to a single spin 3/2 nucleus splits a peak into 4, leading to the 1 to 1 to 1 to 1 quartet observed in the fluorine-19 spectrum. Additionally, boron 11 is only 80% abundant, the remaining 20% being boron 10, which is a spin 6/2 nucleus, which is also coupled to by the fluorine atoms. In that case, you'd observe a septet comprising 7 peaks of equal intensities at approximately the same chemical shift, but with different and generally smaller J coupling constants. Since these peaks would overlap with the more intense peaks arising from coupling to boron 11, they're often not observed, though can be seen in this proton NMR spectrum of a borohydride compound measured on a high-field instrument. As I've already mentioned, one of the features of quadrupolar nuclei is that J-couplings are not always observed. In this case, the tetrafluoroborate spectra shown were obtained in water. However, if the spectra are obtained in acetonitrile, no coupling is observed, and the signals appear as singlets in both the boron 11 and fluorine 19 spectra, except there's 2 peaks in the fluorine 19 NMR spectrum. This is because the chemical shift of the tetrafluoroborate anion is marginally different by approximately 1/20th of a ppm, depending if there's the 20% abundant boron 10 or the 80% abundant boron 11 in the molecule, demonstrating how in the right systems, NMR spectroscopy can quantify isotopic abundances. As a quadrupolar nuclei, the line width of peaks in boron 11 NMR spectra are strongly dependent on the size of the molecule and symmetry around the boron center. While the highly symmetric small tetrafluoroborate anion has line widths of less than 1 Hertz, this 4-coordinate tetraaroborane, a true non-coordinating anion used in chemical and electrochemical research, which, while still tetrahedral around the boron center, is a much larger molecule, gives a peak with a line width of around 20 Hertz. In this case, the data obtained on the X-pulse at the top is compared with that of a nominally identical sample obtained on a modern high-field instrument below. In both cases, the measured line widths are identical. The signal just appears to be sharper at higher field because the data is plotted on the chemical shift scale. So for the X-pulse data, 1 ppm is approximately 19 Hertz, while for the high field data, 1 ppm is approximately 160 Hertz. There's one more thing to notice about these spectra. While the data collected on the X-pulse has a flat baseline, this is not the case for the data collected on the high field instrument. This is a common issue in boron 11 NMR. Since many glasses contain boron, it's not uncommon to observe a background signal in boron 11 NMR spectra due to glass components of the probe and often the NMR tube itself. Though this can be eliminated by appropriate probe design, choices of experimental parameters, and the use of boron-free or quartz NMR tubes. This can happen not just in boron 11 spectra. I've personally observed background signals in both fluorine 19 spectra, likely from PTFE, and silicon 29 spectra, again from the glass, when previously working with high field instruments. The boron 11 spectra we've looked at so far were of compounds with tetrahedral and therefore highly symmetric boron centers. To see what a difference a low symmetry boron center makes, we can consider this spectrum of a substituted phenylboronic acid pinnacle ester, one of a family of compounds using a range of palladium catalyzed reactions. In this case, this fairly small molecule with a 3-coordinate trigonal planar boron center gives a single peak with a line width greater than 200 Hertz. The next 2 nuclei we'll look at are lithium-7 and sodium-23, which have a similar range of applications and performance in NMR spectroscopy. Lithium-7 and sodium-23 are both high abundance quadrupolar nuclei with high receptivities. Solutions of the lithium or sodium cations will generally give signals around 0 ppm, though organometallic compounds of lithium and sodium extend the spectral windows to around 35 and 70 ppm respectively. Recent reports have demonstrated how quantitative NMR methods can be used to accurately measure the concentrations of highly reactive organolithium compounds, a more accurate and safer method than traditional titration techniques. The accurate measurement of sodium content in food, meanwhile, is a valuable nutritional measure which would also be possible by NMR spectroscopy. One of the major commercial uses of lithium is in lithium-ion batteries. In order to accurately model the electrochemical processes in batteries, knowledge of the physical properties of the various components in the battery is necessary. One important property is the diffusion constant of the lithium ions in the electrolyte. Diffusion constants can be directly measured using NMR spectroscopy, using experiments such as the pulsed field gradient spin echo, or PGSE sequence, results from which are shown here. This slide shows PGSE spectra of the lithium cation in a common solvent system used in batteries, with the spectra obtained at a range of gradient strengths. Integrating the signals shows how the peak area decreases with increasing gradient strength. By then considering the gyromagnetic ratio of the nucleus and the parameters used in the NMR experiment, the diffusion constant can be directly calculated. Since the X-pulse can collect spectra at variable temperatures and diffusion constants will vary with temperature, it is particularly valuable to characterize diffusion at appropriate techniques for the individual application. NMR spectroscopy isn't just limited to the S&P blocks. The next NMR active nucleus we're going to look at is a transition metal, cobalt-59. While cobalt-59 NMR spectroscopy is fairly uncommon, though still useful in organometallic and coordination chemistry, and for the study of cobalt-containing metalloenzymes, it holds a special place in the historic development of NMR spectroscopy. As I alluded to earlier, one of the early applications of nuclear magnetic resonance was for the accurate measurement of the gyromagnetic ratios of the different elements and their isotopes. When cobalt complexes were first studied, remarkably large differences in gyromagnetic ratios were observed between different cobalt complexes, significantly greater than observed for other nuclei, or that could be readily explainable by the limitations of the early generation NMR instruments. It was this variation that was termed the chemical shift. Cobalt-59 has the largest spectral window of any NMR active nucleus, with a chemical shift range of plus 14,000 to minus 4,000 ppm, which can be observed as a single experiment on the X-pulse over the resulting 256 kilohertz spectral window. In the case of the two octahedral cobalt-3 complexes shown here, cobalt tris ethylene diamine and hexacyanocobaltate, there is an approximately 7,100 ppm difference in chemical shifts between them. Another transition metal with an isotope amenable to analysis by NMR is platinum. With one medium receptivity, 36% abundant spin half isotope, platinum 195, which can be observed over a wide spectral window. Platinum-containing compounds have a wide range of applications as homo and heterogeneous catalysts and in pharmaceuticals, particularly as anti-cancer drugs. For example, this half-sandwich platinum-4 compound shows a single sharp signal in the proton-decoupled platinum 195 spectrum. Because platinum 195 is 36% abundant, coupling to it can readily be observed, as shown in this platinum-coupled proton NMR spectrum, where both methyl signals have distinct satellites, resulting from the 36% of molecules containing platinum 195, where the methyl signals are doublets rather than singlets. To further prove these platinum satellites, it's possible to obtain a platinum decoupled proton NMR spectrum, which eliminates any splitting caused from coupling to platinum, where both methyl signals will now appear as singlets. Not only can both proton-coupled and decoupled NMR spectra be obtained, the converse is also true, where we can obtain proton decoupled, and proton coupled platinum 195 spectra. While the proton decoupled spectrum gave a single sharp peak in the proton coupled spectrum, we can see the signal appears to split into 6 peaks. In fact, the signal has split into 10 peaks, with the outermost indistinguishable from noise. This results from coupling of the platinum to the 9 equivalent protons of the 3 equivalent methyl ligands, demonstrating how platinum 195 NMR spectroscopy can not only distinguish individual compounds, but can also provide information about the structure of these compounds.
We're now coming to the end of this webinar, so to summarize what we've talked about, NMR spectroscopy can be performed on an extensive range of nuclei, covering almost the entire periodic table. The X-Pulse Broadband benchtop NMR spectrometer can observe 31 different elements in its standard configuration. Applications for broadband benchtop NMR spectroscopy include structural elucidation, sample characterization, quality control, and measurement of physical properties. If you're interested in finding out more about how these sequences and many others may be used in conjunction with the X-Pulse to solve your analysis needs, please don't hesitate to contact us. Our international applications team will be happy to work with you to see how X-Pulse can help you, possibly even in person at one of these events we are attending this year. We'd like to thank you all again for your time and Chemistry World for hosting this talk. There's more information on the X-Pulse and its applications on our website, and if you're interested in future events like this, please follow our LinkedIn page. Robin and myself would now be happy to answer your questions.
Brilliant. Well, thanks very much, Claire and Robin, for some really excellent presentation about NMR. I think we've all learned something today. I certainly have brought back a few memories from some of my undergraduate courses at university. We've got several questions coming in. I'm going to start with a fairly general one, which is at the start of the talk, you said all of the spectra are taken on a single instrument. Can you give us an idea of how easy it is to switch nuclei on the X-Pulse? So, I mean, I've vague memories of talking to NMR technicians from university saying they have to get spanners out and do at the bottom of the machine, but I'm guessing it's a bit easier than that now.
It is somewhat easier to do now on the X-Pulse. I certainly just trying to make sure this video actually starts to play. As a true broadband system, on the X-Pulse, switching between nuclei uses a process referred to as tune and match, and is both quick and easy, as shown in this video where I simultaneously switch both channels, changing from proton phosphorus to fluorine boron. On all NMR spectrometers capable of observing multiple nuclei, switching between nuclei entails more than just changing the radio frequencies transmitted and received. It is necessary to optimize the electrical properties of the probe for each nucleus and ideally for each sample, through optimizing the properties of the electrical circuits. This is achieved on the X-Pulse by inserting 1 or 2 fixed capacitors, which are the black rods, with each combination covering a range of NMR active nuclei. Then adjusting 2 variable capacitors per channel to tune the circuit and to maximize the power transfer of the transmitter and receiver, which is indicated in our SpinFlow software by ensuring that the minima in the curves are both centered, indicating that the circuit is tuned to the correct frequency, and as close to 0 as possible, to match the power transfer to the receiver circuit. This is a rapid and convenient process, usually taking between 2 and 3 minutes to switch between both proton fluorine and X nuclei. The fact that the X-Pulse has this capability in order to tune and match on individual nuclei isn't just applicable when you're looking to switch between individual nuclei. It's just as relevant when you're using a single nuclei, but looking at a range of distinct samples, where the optimal tuning and matching, and therefore the best possible performance of the spectrometer occur under different conditions. A particular example for this might be, as when collecting simple proton NMR, that the optimal tuning position will be different when you're looking at a simple small molecule organic, perhaps in chloroform or similar, and when you might be looking at a highly polar system, such as something with high salt concentration like a battery electrolyte, or indeed an ionic liquid. And systems with a fixed tuning can never give equally good performance of both those classes of sample. Yeah, okay. So in principle, it's exactly the same as you might have done in the past, involving crawling around underneath a high field magnet with a set of spanners to try and do it, except you're doing this on the top of a board of a benchtop instrument immediately next to your computer. It can take, depending on which nuclei you're switching between, anywhere between 30 seconds to probably 3 minutes.
Okay, thanks very much. That's really good.
Right.
So let's have a look at some of the other questions. We've got quite a few questions coming in about the kind of I guess the mechanics of the machine. Can you give us a bit of an idea about the temperature range of experiments that you can run on the machine, and the sensitivity, and what kinds of special spectra you can run, like correlation spectroscopy, some of the more specialist experiments that Claire was talking about?
We went through a fair number of combinations. So in terms of temperature range, the X-Pulse operates as a true variable temperature instrument in the same way as you might be familiar to from benchtop systems. So that is, it operates in variable temperature mode by temperature controlling the sample by flowing temperature control gas supply through. This is particularly important with benchtop systems in general, because anything that's a permanent magnet base, the magnet itself is incredibly temperature sensitive. Its performance is hugely temperature sensitive, for which reason we actually control our magnet temperature to a precision of about the thousandth of a degree centigrade. So we maintain a magnet temperature and then vary a sample temperature. With the standard variable temperature system we ship, we will guarantee actually I think that's no longer what's on the slide is no longer the temperature range we're guaranteeing. We are guaranteeing a temperature range of between 0 and 65 degrees centigrade for sample temperature. In practice, I've pushed it slightly further in both directions, but ultimately it's a limit on your ability to control the gas supply while maintaining the magnet temperature stable. There was something else there in terms of sensitivity. So signal to noise, if we go with a full broadband probe, we're guaranteeing a minimum of 130 to 1 on a 1% ethyl benzene sample. If you're only concerned about proton and fluorine and aren't interested in the X channel at all, we can actually go higher than 200 to 1 signal to noise. So if you're only particularly concerned about very low sensitivity carbon or fluorine, you can get a 2-channel only probe. In terms of pulse sequences, in principle, anything that you can visualize running on a high field system, we are in principle capable of running on the X-Pulse. In practice, realistically, we'd run as a standard mode, we'd run obviously a full range of simple one-dimensional spectra. We've seen depths today, we've seen HSQCs today, we've seen HMBCs today. We do a lot of solvent suppression work, so we take advantage of gradients and shaped pulses to do sort of solvent suppression using wet, selective toxies, selective noses, obviously the pulse field gradient spin echo and the associated dozy sequence for measurement of diffusion constants. and that's just off the top of my head. If there's something very particular that you are interested in, that we can obviously either establish it's already ships with the system, or very much looking to develop those pulse sequences in the future. And I'm sure the more sequences we have that we can have to develop, the more Claire's got to do every day.
Excellent. And just to follow on from that, can people develop their own pulse sequences on this instrument? Can you get in there and do things yourself, or is it very much working with Oxford Instruments to develop those sequences?
So there's both options. So the pulse sequences are written in Python. So the instrument comes with software that lets you automatically delve into the sequences, but equally we're interested in working with people to develop new sequences as well. So both are options. In the vast majority of cases, though, the sequences that the systems ship with tend to be sufficient for most people.
Yeah, absolutely. Okay, just as a follow-on question to some of what you were talking about with sensitivity, Robin, can you give us an idea of what that sensitivity translates to in terms of kind of how much sample you might need for typical sorts of experiments? Obviously, it depends on how.
It depends an awful lot. So, as a guide, it depends on a guide. It depends on how long you are willing to run your typical experiments. So let's say we go for a proton experiment, we go for around 16 scans, which is generally fairly standard, not just at benchtop, but up to high field. We're looking at a detection limit of probably about 1 millimolar concentration. We're looking at a quantification limit probably somewhere between 5 and 10 millimolar. Obviously, we can go to lower concentrations if you're happier to run longer experiments. Obviously, generally, this is protons, so everything else is going to be worse. Carbon, very much so, I would say you can run carbon. The carbon spectrum we showed here was probably a 1 molar solution, and they'd have been obtained in under an hour. I'm not willing to guarantee exactly which ones they were without looking closer at the original metadata.
Okay, no, I think that's a good sort of ballpark for people to get an idea if they're familiar with what they're talking about. Okay.
If you're doing an actual product synthesis and you are routinely generating milligram quantities of compound, you run it on the highest field system you can. But if and when you're making gram quantities, or quite frankly, ton quantities of compounds, you can run your carbons, and quite frankly, if you're making ton quantities of compounds, you could run run a neat sample with an external lock and get a carbon spectrum in 5 minutes.
Brilliant. Okay, thanks very much. Okay, so I think we've probably got time for one last question, which is we talked a little bit about maintenance of the machines. I mean, you talk about the high field machines needing cryogenic gases and all kind of things. Can you just give us a little bit of an idea of what's required to maintain one of these benchtop systems?
So essentially the main requirement that you have is that you have somewhere that you can plug them in, basically. In terms of maintenance, I guess the most exciting maintenance happens if you break a sample. Then you would need to remove the probe and clean it, but that's you don't have to send the probe off. That's very easy to do in-house. Anything that you would like to add, Robin?
I think that's pretty much it. That thing is, these systems generally don't require maintenance. We've had the predecessor system to this, which is the Pulsar, which is probably nearly 10 years old now. We've had these systems out in the field for a year, for most of those 10 years, and generally the thing that's most likely to be a problem is eventually the PC they're plugged into dies, and the old installation of Windows is no longer supported. More than anything with the hardware, the only literally the only routine service that these systems require is there's 3 or 4 fans on the back of them that are just standard PC fans you might find on a PC case, and we recommend the filters on them are cleaned every couple of months. So it's nothing like any sort of high field systems where you've got to worry about taking them out of service once a week for hydrogen fill, not nitrogen fill even.
Yeah, I was going to say filling them with hydrogen could lead to some
It
interesting
could be,
activity.
yes. I think the helium quench videos that you can find are spectacular enough.
Yeah, definitely. And I guess most of that comes down to the fact that it's a permanent magnet rather than a superconductor.
Exactly, it's a permanent magnet. Once the magnet's there, the magnetic field is there, is stable, and beyond that, you're just working with electronics.
Brilliant. Okay, well, I think that is absolutely fantastic. We have covered a great deal of stuff. There are a couple of other questions that have come in. I think any of those that we didn't get through to, we'll go through to Robin and Claire after the webinar, and they will be able to respond to them by email afterwards.
Yeah, so yeah, indeed. Everything else, all the other unanswered questions, we will respond to. Since, as you may have noticed, we're both at a conference on Thursday and Friday, it won't be till sometime next week.
Absolutely fine. Okay, well, I think that gives us a good point to draw this to a close. So just to thank Claire and Robin again for a really interesting presentation and some really good answers to the questions that we've had. Thanks to Oxford Instruments for sponsoring the webinar, and thanks to you, the audience, for coming along, sharing your time with us, and for sending us in some really great questions. Just a reminder, you will get an email with a recording of the session in a few days' time. You'll get a certificate of attendance in that same email. And if you like this webinar, do remember to check out chemistryworld.com/webinars to see what other topics we've coming up soon. And I hope to see you in another webinar very soon. My name is Philip Broadbent. I'm Chemistry World's business editor, and goodbye for now.